Hello, everybody. Can you hear me?
Yes.
Okay, so now we will go back again to this nice example. We need to classify non-separable data set. Non-separable data set, which requires a very complex model. You will just imagine, I mean, if your data set is really very complex, you need to build a very complex model. So when the data set is, because it's data driven, we try to build this data driven model. So when your data set is complex, we should expect that your model will be complex. But in fact, we can spend some time with the data and try to engineer some features to make it simple. So this is an example. We will use this function which is called the make circles. We import it from sklearn.datasets. We need also to use a logistic regression model, which is very simple one. So first we need to generate my data set. We need to use this function, make circles. We need to define number of samples. So for example, number of samples equal 500. And this is also the amount of noise, right? When you increase this amount of noise, there will be some overlap between these two classes. I mean, this function, it generates two classes. It's called the make circles. It will generate those two circles inside each other. So we have the red one and we have the blue one. And when we need to classify, it's binary classification problem, as you can see, because we have only two classes. We have the blue class and the red class. We need to build a model which can classify those two classes into two separate classes. So in reality, we need to generate this line, right? I need to select maybe another color. We need to maybe not blue. We need to have this kind of decision boundary, right? We need to have this decision boundary, which is very complex, and it's not linear because it's a circle or it's a curve, so it's non-linear in fact. So we need to get this line. Can you propose a solution, please? Can you propose a solution? What do you think? We need to generate this decision line or boundary which can classify the data set into blue and red. And the data set is very simple. We have only two features. So if we need to put this data set into a table, for example, it will be like this one. We have X1, and we have X1, we have X2, and this is Y, target feature, right? So maybe the red one, it will be zeros. And after that, the blue one, it will be one like this. So the data set is very simple, right? This amount of noise, it will just make it also challenging if you want to increase the overlap between the two classes, just increase the amount of noise here, right? So can you propose a way for solving this problem? How can we solve it?
Sorry, can we, for example, I don't know.
Sorry.
I mean,
yes.
Can we, for example, do some kind of dimensionality reduction or transformation to like make these kind of features like linearly separable?
Yes, we need to do this exactly. We have two classes, but maybe not dimensionality reduction because we have only X1 and X2. So maybe you need to, reduce it into just X1, for example. So it will be one dimensional. So it could be. So anyway, we need to work a little bit with those features to try to find a way to make it separable, right? We need to make it separable. So we can.
Sorry, I was thinking distance because if we can actually have check if the difference between every Y of the sample is less than, for example, something, then it goes to the same class. And then I was considering that we should somehow to define the distance between y0 and y equals 0 and y equal 1.
Yeah.
So divided by half.
So we can move it from this maybe Cartesian coordinates into another coordinate system. For example, we can represent it in a different coordinate system, and in this case, maybe it will be easy to classify it. So, for example, here We can make it separable, for example, by adding a new dimension, not in fact dimensionality reduction, but we need to add a third dimension. And in this case, it will be easy to classify it. For example, when it's in two-dimensional space, it's inseparable because it's difficult to find a straight line which will classify it. If I need to use a linear model, maybe we will do a line like this one, right? So in this case, maybe all data points above it will be classified into one. So that part will be correctly classified, right? This red part, because it's one. This one, it will be wrongly classified when y equals 0. So this blue part, it will not be correct, but the blue part here, it will be correctly classified, right? So if we draw this line, so maybe the accuracy in this case will be, maybe, I don't know, 20%, 25% or something, or maybe 50%, because that part is correctly classified. That part is correctly classified, right? And also that part is correctly classified. Other data points are misclassified. So straight line will not work with us when it's in two-dimensional space, but maybe one solution is to try to find a super feature which can help us to make it easy to classify. So for example, we can add x3, for example. We can add a third dimension. And this third dimension, it could be, for example, x1 squared plus x2 squared. For example, this is feature engineering. So we need to engineer a feature which can give us an advantage. So we need to generate a new feature or add a new feature which will help us to solve this problem easily. So we need to add x3 here, and then when we add x3, in this case, we will plot this example in three-dimensional space. So we have here x1, we have here x2, we have here also x3. So maybe if we added x3 equal x1 squared plus x2 squared, maybe in this case it will be separable because we can plot this plane. So as you can see here in this graph, we can have this decision line. So the decision line will be this plane, correct? In this case, all blue points will be above the line and all red point will be below the line. And in this case, we can classify it. But in this case, we increased the complexity of our data set because we increased the dimension. We added one more dimension to make it easy or make it separable. So we added this higher order feature, for example, higher order feature. This higher order feature, it could be a combination of different interactions between x1 and x2. It could be x1 times x2 plus x1 squared plus x2. We need to find a way to get this creating x3. But this is one way for solving it. It's not to reduce the dimension into x1, but adding a new feature. So we can represent the data easily. It could be separable in a higher dimensional space. So now we are moving it from two-dimensional space into three-dimensional space by adding x3. And the x3, we need to find how can we construct x3 using x1 and x2, using the information provided by x1 and x2. One way is a proposal, for example, it could be x1 squared plus x2 squared. And in this case, it will be separable in higher dimensional space. And instead of building a model, if we are using a perceptron, for example, so instead of using only x1 and x2, we will add another feature, which is x3. And in this case, we can just use a perceptron for classifying this problem easily. And this perceptron should be able to generate this plane, correct? Which will divide the data set into two different classes, 0 and 1, 1 above and 0 below it. Yes, maybe each time I need to clean. Yes, so in this case, we will build a model. Do you see here? We need to use a perceptron for solving this problem. So it will be, we have three inputs, x1, x2, and x3. x3 equal x1 squared plus x2 squared. We will use a perceptron, so the decision plane or the decision, it will not be a line, but it will be a plane. It will be omega 1 x1 plus omega 2 x2 plus omega 3 x3. So we added the part here, plus b, right? So we have this example in this link if you want to check it. But I wish to do it in a different way, in fact. So I want to fit a logistic regression model for higher order feature. We will use a higher order feature, but also we will try to keep it in two-dimensional space. So I will create this feature. We created this new feature here, which is x1 squared plus x2 squared, right? So we created new one. x1 square. No, sorry. In this example, instead of using x1 and x2, I will just use x1 square and x2 square. So my data set was like this one, right? We have x1, we have x2. I will just use x1 square and x2 square. We have here is a target feature, right? So I will use this one instead of using the original x1 and x2, because when it's x1 square and x2 square, it will give me more advantage, because we can generate, instead of generating a line, we can generate a circle. So my decision line, instead of being a straight line, it could be a circle. So instead of using x1 and x2, I will use x1 square and x2 square. So x will consist of x1 square and x2 square. I defined my model here, logistic regression. So the target feature will be x1 square and x2 square. And the target feature, of course, it will be the same y. And y predict, it will be model, don't predict. I didn't divide my data into train and test. I will just use the whole data set here. So I will apply x again to the model predict to predict y predictions. And I will print model coefficient and intercept. So those coefficient and intercept, it will be for x1 square and x2. So I will plot my model here. So my perceptron will be like this one. I will use here x1 square, and I will use here x2 square instead of x2. We have here x1, omega 1 and omega 2. We have here bias. So the decision line, in fact, it will be omega 1 x1 square plus omega 2 x2 square plus p equals 0, right? After training my model, we found that omega 1 equals this number, omega 2 equals this number, and this is bias. So just substitute those values. So I will get this equation, right? So it will be minus 8.17 multiplied by x1 square plus x2 square. Take minus 8.17 as a common factor. So it will be like this one, plus 6.71, which is the bias. You can move that part to the other side, multiply both sides by negative, divide by 8.17. So finally, the decision line will be like this one, x1 square plus x2 square equal minus 0.2, minus, 0.82, which is 0.91 squared. In fact, this equation, x1 square plus x2 square, it's equal r square. This one is r. It's the equation of a circle, right? It's an equation of a circle. So we will get those coefficients. If I want to plot this circle, I will get x1, right? And after that, I will get x2, substituting for x2 from this equation. But it will be squared, in fact, right? So I have this, we have x1, right? I have x1, and I will get x2. It will be the coefficient of, it will be omega 1 multiplied by x1 squared, you see, right? So, so I want to get x2, right? So x2. So it will be from this one. I need to get x2 squared. So x2 squared, it will be minus omega 1 divided by omega 2, correct? It's all divided by omega 2, right? Minus b, the intercept, divided by omega 2. So in this case, we will get x2 squared. So now I have, in fact, and of course, x2 equals square root of x2 squared. So I have x1, we have x1, I will have x2 squared, x2 equal x square root of x1, right? And I will plot x1 and x2 in this case. When we are plotting x1 and x2, we will get this beautiful circle, right? And it's a perfect circle which will divide those two classes into two separate classes. So this example, in fact, it shows you that if we can spend some time working with features, try to find a super feature, it will help us to simplify our model. So now instead of using x1, instead of solving this problem in this way, okay, so instead of solving this problem using by adding this higher dimensional feature, higher order feature. So we can just say that this is higher order feature, right? And we changes the dimension of the problem from 2D into 3D, which is more complex now, and generating this very complex plane, for example, right? we can just simplify it by try to work a little bit with the features and try to find a super feature which can help us to simplify our problem. So if you want to find, we have the coefficient. If you want to calculate the error, of course, it will be the difference between y minus y predicts. So this is the error, y minus y predicts. This is the mean value, or if you want to square it, you can square it and just get the mean squared error. So this is y minus y predict, which is the error. But in fact, I mean, maybe the best way for calculating this error value is to square it, because maybe some positive and the negative values will remove each other. So this is very dangerous, in fact, to calculate the mean error, but it should be mean squared error, right? Because maybe the first example, it will be 0.5, the second example will be minus 0.5, so it will be a problem, right? So it's much better to square this number. And after that, we plot x1 and x2, so we will get this beautiful circle, and also using a scatter plot for plotting class 1 and the class 2. So to visualize the data set in a higher order feature space, I can also plot it in x1 square. I mean, because in fact, the model, our model, shows the data like this one, because we used x1 square and x2 square here, right? So if you want to plot your data against x1 square and x2 square, it will look like this one, which is very easy. And in fact, when we use the perceptron, we just try to generate this beautiful line here, right? Oh, sorry. So we got this line. Okay. I'm just starting my share my one more time, yes, please. Okay. Can you see my screen, please?
No.
It's just black.
Yeah, it's a black. Yes, I don't know why.
Now it's fine.
Okay. So it's strange. When I share, when I maximize it, it becomes dark. Yes. Yes, maybe it's working now, right? Okay. So I mean, for the model, in fact, when we use this approach, when we use x1 square higher order dimensions, higher order feature space or something, so when we plot our data set against x1 square and x2 square, it will look like this one, which means the model will see the data like this one, and when we use a linear model, it will generate a decision line which is like this one. So this is my decision line, but in fact it's function of x1 square and x2 square. So the equation of this line, in fact, it's omega1 multiplied by x1 square plus omega2 x2 square plus p equals 0. So this is my decision line, which is completely straight line in this higher order feature space. So this decision line will be linear, or it will be a line in this higher order feature space, because I'm plotting my data against x1 square and x2 square. And if you want to, I mean, make it easy for people to understand, so just to try to plot it against x1 and x2. When you plot it against x1 and x2, it will be a circle like this one, right? And it's because this is the equation of a circle, because it's equation of circle, right? So in fact, it's x1 square plus x2 square equal r square. This is the equation of a circle, where r is the radius of this circle, right? So this example, it's a nice example because it will show you that if we can spend some time, try to work with feature engineering, try to find a super feature which can help us to simplify our problem, we can really reduce the complexity of the model and try to get very, very good results in short time. And for explainable AI, for example, it's not black box model because it's easy to understand. We just use a perceptron. We understand it because we understand the meaning of omega 1, omega 2, and p, right? So the model will be simple and we will get very good results. And this model will be able to generalize easily. It will not overfit my data. So logistic regression, I need to repeat here, is this logistic regression for logistic regression was iris example. It's the same, we did that several times. Logistic regression, we need to import it from linear model. We need to use this standard scalar. We need to upload our data set. It's just a standard process now. We need to upload our data sets from sklearn data sets, for example. You need to select which features you want to get. You need to use standardizations or standard scalar, whatever. So now this is the original values, this is the range of the values. So you can print it after doing this standard scalar, for example, to see the range. We have 3 classes, 0, 1, and 2. We will use a logistic regression. Random state equal 1. I don't remember what does mean C equal 1. Logistic regression. We will use XY for training the model. We will use X for calculating Y predict. From Y predict, we can calculate mean squared errors. This one, it's now mean squared error. Please try to make it squared all time. It's more safe. Or you can get also the same value, in fact, by counting number of cases where Y does not equal to Y predict. So this is number of misclassified example. This is the number of misclassified examples or misclassification. So printing the model parameters, we will get those weight values, right? How many classes here? It's a logistic regression with iris. We have 3 classes. We have 4 inputs, so it will be 4 times 3. So the dimension of this matrix, in fact, it's 3 times 4, but it should be 4 times 3. It's 4 times 3. 3, it's number of classes. And 4, it's number of input features. Right? And we have those bias values. It should be 3, correct? This is the bias. So if we need to plot this model for this iris data set, it will look like this one. So it will be like we have 3 classes, correct? So it will be T1, for example, T2, T3. And how many inputs? We have 4 inputs. We have X1, we have X2, we have X3, we have X4, and just make those connections, right? It will be like this one. So it's like feed-forward neural network, but we use the logistic regression model in this case. The accuracy here, as you can see, is accuracy. It's 26%. It's very, very strange. It's mean squared error. In fact, this is the mean squared error. It's 0.26. We need to multiply this one by 100, so it will be 2.6. So this one will be 2.6%. 2.6%, which means the accuracy will be 100 minus 2.6, which will be 97.4%. Number of misclassified cases equal 4. This is the number of misclassified cases. If you get the accuracy in a different way, it should be 4 divided by the size of the test set, which is 100, correct? 150, sorry. So it will be 4 divided by 150. It should give you the same ratio, 2.6%, right? So which means that 22.6% of the cases are misclassified. So it's now we can use logistic regression with for classifying iris datasets. Okay. Yes. I was giving people an example, logistic regression, but I mean, we solved it already, right? So try to implement a perceptron to classify iris using SCK scalar, for example. So it's, I mean, last time we used logistic regression, try to use a perceptron. The pre-processing standard scalar, is there any difference? No. You just try to implement logistic regression, convert adaptive linear unit into a logistic regression. So adaptive linear unit, we use it for regression problems, but if you want to use it for classification problems, you need to define a threshold, right? This is the training set, and we have two classes, 0 and 1. For it's for adaptive linear unit. We have hypothesis. We have this function. We need to define a cost function, and we need to find a way for updating the weights. So delta omega, we need to calculate delta omega, and the delta omega, it will be minus theta multiplied by the gradient, which is partial j by partial omega. J, it's the squared error, correct? So it's 1 divided by n multiplied by this 1. And we can just find, I mean, we did that already for the adaptive linear unit. For iris dataset, this is iris dataset for the first two classes. I don't know why. Okay, scalar dataset. So this iris dataset, we have two classes, feature 1 and feature 2. Logistic, I just ask you to use logistic regression for this problem, but we use adaptive linear unit or a perceptron. This is the example which we did last time, but in this case, we use it with Gaussian activation function. Because a perceptron, we use step function. But if you can replace the step function with a Gaussian, it will be adaptive linear unit. But we just can skip that part. So for, okay, we are going backward. Okay, so now we need to talk about, so we used it for classification, and we can, I mean, this is the example which we have from last time, if you want to implement it. Because here we defined logistic regression. We defined, I mean, if we need to go through the code, I mean, we defined a class called the logistic regression, for example. Number of epochs equal 100, learning rate equal 0.1, for example, random state equal 1. And fit for fitting and training my model. We need first to get this random state. We need to generate weights and the bias, right? From in this way. And after that, we will, for each epoch, we will calculate net, which is omega x plus bias, omega x dot product, omega x plus p. We need to apply this net to the activation function, which is Gaussian. So output will be 1 divided by 1 plus exponential minus net. So we calculated the output. We will calculate the error. So the error will be y minus output, or target minus output, correct? Predictions. Update weights. So delta omega. So omega equal omega plus delta omega. Omega would be eta multiplied by input multiplied by the error. For the bias, it will be just error because the input equal 1. After that, we will calculate the cost. It will be the mean error. Yes. Yes. So we can just go. So now we need to talk about confusion matrix. Confusion matrix is very important for evaluating the performance of your classifier. We use confusion matrix for classifications problems. It is used to describe the performance of your classification model or the classifier or a set of tested data for which the true values are known. So it is used for supervised learning because we know, because as you can see here, we have some actual classes against the predicted classes. So we need to know the actual classes. So the confusion matrix, it's a table which is often used to describe the performance of a classification model or classifier on a set of tested data for which the true values are known. So if it is binary classification problem, for example, we have those actual classes. We have positive, negative, correct? So so we have those actual classes against predicted classes. If it is binary classification problem, we have positive and negative, for example. So when it's positive and predicted as positive, we call it true positive. So when the actual class is positive and the predicted one is positive, we can just say this is a true positive. True positive. When it's negative and classified as negative, we can call it true negative, right? When it's positive and classified as negative or misclassified as negative, we can say that it's a false negative, correct? Because it's positive, but it is misclassified as negative. So we need to call it, or we can call it false negative, FM. When it's negative, but it's misclassified as positive, we can call it false positive. Because it's originally negative, but it's misclassified as positive, so we can call it as false positive. False negative, it's called the type 2 error. And false positive, it's called type 1 error. Which one is more dangerous, type 1 error or type 2 error?
Type 1.
Why?
Because it's better to have some false alarms than to think that everything is okay and it's actually not.
So false alarm, which means he is negative, but he is classified as positive. So this is false alarm. It's better to get false alarm instead of.
Yeah, correct.
Right?
Sorry, I meant the opposite. Type 2 is.
Yeah. So in fact, the type 2 error, it's more dangerous because he is positive, but he is classified as negative. So we have fire, but we cannot classify it as a fire, for example. Correct?
Exactly.
So it's more dangerous, in fact, to have this type 2 error. Type 2 error is very critical, especially in medical domain. So when you read a paper in medical domain, for example, or medications, for example, they are testing a new drug for COVID or something, type 2 error is very, very important. This number is very, very important. Or a device, for example, they are building a new device, and this device will be used for diagnosis, for example. So they care a lot about type 2 error. So type 2 error, it's false negative. We have also something called, for example, accuracy. So the accuracy of, this is a total accuracy. It will be total positive across, in fact, we need those numbers across the diagonal. We need to maximize those numbers. So the numbers across the diagonal, we need to maximize it, because if true positive is 50% and the true negative is 50%, this one 0 and this one 0, for example. So in this case, the accuracy will be 100%. So the accuracy will be true positive plus true negative divided by all other numbers. True positive plus true negative, true positive, true negative, false positive, and false negative. So this accuracy will be the accuracy of my model. We need to maximize, we need to increase this one, right? If you want to increase this accuracy, we need to increase the numbers across this diagonal and minimize the other numbers, right? We need to minimize this one, we need to minimize this one. So type 1 error, type 2 error, we need to minimize, but type 2 error, it's more dangerous than type 1 error. So this is the accuracy. We have also precision. So precision, it will be true positive divided by true positive and false positive. So this is the precision. It has a definition, in fact. Maybe in the next page, we will have the definition of what is the meaning of precision. Sensitivity, or I guess sensitivity or recall, right? This is the true positive cases divided by true positive plus false negative. And it means, I guess, it's a true, it's a true positive which can be classified as positive. We will go to the definition. So true positive, these are the cases in which we predict yes. For example, they have the disease and they do have the disease, for example. So some people, they got COVID and they did this test, for example, in the hospital, and they are classified as positive, right? So this is a true positive. He has a COVID and he is classified as positive, right? True negative, we predict no, and they don't have the disease. He does not have, he is negative COVID, and he has been classified as negative, which means it's fine. It is true negative. False positive, we predict yes, but they don't have the disease. He is false positive. He is negative, but he is classified as positive, right? Which is type 1 error, false positive. So false positive, he is negative, but he is classified as positive. So for example, someone he does not have, he has a common cold, for example, and he went to the hospital and he did this COVID test and they found him positive. So they will ask him to stay at home. Don't contact other people, maybe drink hot stuff and relax, for example. So there is no harm, in fact, from this type 1 error. We will just be cautious, be careful about some people. We just ask them to relax, maybe take some medication. Of course, it's not correct to take some medications, but it's much better than type 2 error, where someone is false negative, right? He is positive, but he has been classified as negative. So he has COVID, but the device said that no, he is negative. So in this case, we will ask him to go to work, meet other people, spread this COVID among other people. So this is more dangerous, which is type 2 error. We have this prediction error, which is a sum of all false predictions divided by total number of predictions. So it will be false positive plus false negative divided by all numbers, the prediction error. And it's the opposite of the accuracy, because the accuracy will be total positive divided by total numbers. So the accuracy will be sum of correct predictions divided by the total number of predictions. So the accuracy will be true positive plus true negative divided by all numbers, which is 1 minus error. But the error will be false positive plus false negative divided by all other numbers. We have something called the true positive rate, false positive rate, precision, recall. I guess I have updated slides for those stuff. So the accuracy, we have here an example. Imagine that we have this example. So the sample size is 165, and this is the predicted, this is the actual, right? So this is the actual. We have those actual, right? We have those predicted, and we have this. This one, it's a true positive. It's yes, and they classified as yes. This one will be true positive, right? True positive. This one will be true negative, correct? Because he is no and they classified as no. He is no and they classified as yes, so he is false positive. This one yes and they classified as no, so this one is false negative. From those numbers, we have functions. In fact, we have very nice functions in Python which will generate all those numbers for us. So don't need to worry about it. So the accuracy will be true positive divided by true negative divided by total number. So it will be 90%. Misclassification rate, it's how often it is wrong. So it will be false positive plus false negative. This is the error, right? So this is the prediction error, for example, or classification error. So it will be false positive plus false negative divided by total. So it will be 1 minus accuracy, correct? So it will be this number. True positive rate, when it's actually yes, how often does it predict yes? So when it's positive. So it will be true positive divided by true positive by false negative. So this is a true positive rate, which is sensitivity or recall, right? So it's a true number of true positive divided by true positive plus false positive. True positive, false negative, right? So it will be 100 divided by 105. So it's a true positive, which is this number 100 divided by true positive, which is 100 plus false negative. False, because it was positive. Yes, this number. Because in fact he is positive, but he is predicted as false negative, right? But he is actually positive. So it's a total positive divided. It's a true positive divided by total positive cases, right? This number. So it will be this number divided by this number. So this is recall. True negative rate, which is the specificity. It will be true negative divided by actual no. It will be 50 divided by 60, right? Precision, it's a true positive divided by true positive plus false. It's when it predicts yes, how often it is correct. When it's predicted yes, right? When it's predicted yes. So it will be 110, right? True positive divided by 110, which is the precision, right? So it will be true positive divided by total predicted yes, 10 plus 100. So it will be this precision. Again, this confusion matrix, it's only for classification problems. It's not for regression problems. For regression problems, we need to find another metric, for example. such as mean squared error, for example. If we need to get if we need to plot this confusion matrix for from Python, for example, we have this. I mean, we need to this. We need to. So we have those. This is my data set, for example. This is target classes, for example. We have a function, very nice function called the confusion matrix. Confusion matrix. So this confusion matrix is input to this function will be actual y and predicted actual outputs and the predicted outputs, or target features and the predicted features. So it will be y and y predict. So the input to this function will be y and y predict, and you can plot this function. You can plot this matrix, and then when you plot it, you will get this. This is true labels 1 and 0. This one it will be true positive. This one it will be true negative. This one it's a 0 but classified. This is true labels, and this is predicted. Right? So this one predicted, yes. So it's a 0 but it's predicted 1. So in fact this one it's false positive. This one it's true positive. This one true negative. This one it's yes but it's classified as 0, which means it's false negative. False positive it's type 2 error. False negative it's type 1 error. Right? False negative. Oh, sorry, this is type 1 error. Sorry, this is type 1, this is type 2 error. Correct? Yes. Okay, so now we want to talk about error backpropagation. I guess I will have also some. I will try to make something very simple for this error backpropagation, so we can make it easy also. Okay. So now we finished those simple linear models. We need to go to the next step where we can. So this is again single layer neural network. I mean, this one it's like single layer neural network for this. I mean, logistic regression classifier. We need, in fact, the concept here is to we have a cost. We need to define this cost function, right? Again, we need to define a cost function. This is my cost function, which is y minus predictions. Correct? It's y minus predictions. This is the error function or the cost function. It's y, which is the target features minus predictions. This one it's predictions because we have omega x plus p. Just assume it's omega x plus p, and this is the activation function phi. So it's a phi of omega transpose x. Correct. So it will y minus this one. This is the error function. And you know that it's a squared because we need to have this function as convex. We multiply it by 1 divided by 2 because when we differentiate, we need to get rid of this 2 to make it easy for us. And the rule for updating those weights, it will be omega equal omega plus delta omega. And the delta omega will be minus eta multiplied by the gradient. So the gradient, it will be the first derivative of this function for y. So this one, it will be partial j by partial omega equal partial j by partial y multiplied by partial y by partial omega, correct? So partial j by partial y, it will be this one will be constant. So it will be 2. It will be 2 times this one. It will be y. It will be y. Yeah. Partial j by partial y. Partial j by partial y. It will be 2 times this one. Multiplied by y minus phi, correct? Partial j by partial y, it will be that part. Right? And the partial y by partial omega, y equal omega x. So partial y by partial omega, it will be x multiplied by x. So this one will be the rule for adjusting our weights. So we will use the same technique. We will use the same technique with error backpropagation. in case of error back propagation, we need to start, of course, from maybe a simple model. So it could be something like this one. We call it multi-layer perceptron. We call it multi-layer neural network, or MLP, right? So this one, it's a 2-layer. We have this one, we call it input layer. This is, we have here one hidden layer, and this is the output layer. So if you want to use this one with iris dataset, this one will be T1, target 1, target 2, target 3. Those inputs, it could be X1, X2, X3, and X4, right? I mean, this hidden layer size, it's up to you to select. I mean, there is no rule for selecting number of neurons in this hidden layer. So those connections, it will be connected with the hidden layer. So the weights we will have here, weights maybe omega 1, omega 1, 2, until omega 1n, for example, and so on. So we have here weights, it will be matrix omega. The dimension of this matrix, it will be number of inputs multiplied number of hidden layers. So if we have here n, and if we have here m, we have here b, so the dimension of omega, it will be n times m. If the weights here equal v, right? Of course, we have bias here also. Remember that we have bias, right? If this one v, the size of this one v, dimension of v, it will be m times b. And we will apply, we have also here bias, correct? And so when we apply some example, we apply inputs, we propagate until we reach the outputs, we calculate predicted outputs here, we subtract those outputs from the targets, we calculate error, and we go backward to adjust weights. When it's 3 layers, for example, or 4 layers, you can go deep as much as you want, but remember that we will have this vanishing gradient problem when you go deep. So we have input layer, we have the first hidden layer, we have the second hidden layer, we have the output layer. So the structure, I mean, it's up to you to select the structure. It's hyperparameter also. So to select how many hidden layers we need and how many units in each hidden layer, it's a hyperparameter. Yes. So how backpropagation works? Imagine that we have this kind of neural network here. We calculate. We go forward first. We go forward until we calculate predictions. I will call it y predict, for example. And after that, we need to calculate the error. So the error will be y minus y predict, or t minus y predict squared summation divided by maybe n, right? So we will calculate the error, and we will go backward and adjust the weights from the output layer until we reach the input layer. So we're just adjusting this one, for example. It could be v, for example. We need to adjust. We need to calculate delta v, adjust v. So v equal v plus delta v, and we will go to this point here, and we will go to adjust the weights here. It could be omega, for example, and we do it layer by layer until we reach the input layer. So if you need more details, I can prepare more details for error backpropagation. But maybe today we need to use MLP from sklearn, for example, also for classifying iris dataset, for example. So in this case, you need to use MLP classifier. We can use MLP classifier from here, and at the same time also we can use it from Keras. I prefer to use Keras, in fact. So first, I need to upload my dataset. So we need to load iris from sklearn.datasets. I need to use MLP classifier, which is feed-forward the neural network. So this one, it's a feed-forward the neural network. So we need to import it from sklearn.neural network, not linear models, but neural network, MLP classifier. Of course, we need from now on to use train test split or use k-fold cross validation. So we will use train test split from model selection, sklearn.model selections. We need to evaluate my model. So we need to use the confusion matrix because it's a classification problem, correct? And we need to plot this confusion matrix. So in this example, in fact, we will do everything. First, we have our dataset. We have our dataset number one. We need to load. We need to upload our dataset. It could be from a file, or it could be from some datasets from databases, for example. So in this case, we will get it from sklearn.datasets. Model selection, we need to select a model. It could be a perceptron, it could be linear regression model, it could be adaptive linear unit, it could be MLB classifier, it could be a deep learning model. So the model selection is something which you need to decide which model we need to test. It could be a set of models. So now we will select MLB classifier from sklearn.neural network. We need to decide which validation protocol we will use. So maybe we will use, in this case, train test split or k-fold cross validation. If it is train test split, we need to select it from model selection. Confusion matrix for evaluation. I need to evaluate my model using confusion matrix, because this confusion matrix, it will give us access to precision, recall, accuracy, all those numbers. We will get all those numbers from the confusion matrix. So first, we upload our data. So first, we are working with the data. We have our data, and after that, we will. This is the validation protocol, right? This is my validation protocol. We will use hold-out validation. We will stratify, correct? Stratify equal y. It's very important because I have an iris dataset 3 classes, and I want to be sure that all those 3 classes are equally represented in my test and training and test sets. We will use random seed because when we shuffle and split, I need to keep this, because in fact this function train test split, it will shuffle first, and it will randomly select percentage of examples as training, and the rest will be used as testing. The test size here, we need to decide this number here. I selected the 0.2, which means 20% of the data will be used as a test set, and 80% will be, so it will be 80-20 ratio. 80% will be as training, and the 20% will be used as testing set. If you want to be sure just to double check that all classes are equally represented, I can just use this function, which is bin count. Bin count y, bin count y train, bin count. We apply this one to the target feature, because only the target feature can help me to know which one is what. So bin count y, for example, to know how many classes we have, how many examples from each classes, for example, and the bin count y train and the bin count y test. So after that, I will import MLB classifier, and in MLB classifier, as you can see here, we used MLB classifier, model selection, MLB classifier. We need to select the solver, and I used SGD, and SGD stands for stochastic gradient descent optimizer. This is the optimizer or the solver. This is the optimizer or the solver. So we use the SGD, which is a stochastic gradient descent. Stochastic gradient descent. There are other options. For example, you can select this one, for example, LBFGS. So you can select Adam, for example. So I select the SGD, stochastic gradient descent, random state equal 0 or equal 42. This is very important if you need to reproduce your results, because here my model consists of a big number of weights and bias. So I need to randomize, I need to initialize those weights and bias, and I need to be able to reproduce those numbers again. So in this case, you need to define a random seed here, or random state. This one, it's the hidden layer size. In this function, you need to define it in this way. This is the hidden layer size. This one means you have only one hidden layer, and you have 5 neurons in this hidden layer. You have alpha equal 0.5. I don't know what is alpha, in fact. Maybe it's learning rate or something. Maximum number of iterations equal 1000. So if I need to plot this function for my iris dataset, it will be like this one. I will start with the hidden layer. So the hidden layer consists of 5 neurons. So it will be 1, 2, 3, 4, 5. Number of outputs. So from my dataset here, we don't need to specify number of outputs or number of inputs, because this model will be able to figure it from the X train and Y train. When we use this MLB, when I defined my model equal MLB classifier, we just need to define number of hidden layers and the size of each layer, number of units in each layer. So this one, it's one hidden layer. If I selected this one like this one, for example, 10 and 5, in this case, we have 2 hidden layers. Number of neurons in the first hidden layer is 10, and the number of neurons in the second hidden layer is 5. So if you want to have 2 hidden layers, you need to define it like this. If you need to have 3 hidden layers, So it will be, for example, 10, 5, 4, for example. In this case, we will have 3 hidden layers. Number of neurons in the first hidden layer will be 10. The second has 5, the third has 4. So we will go back to my example where we have 1 hidden layer, and this hidden layer has 5 neurons. And number of outputs, it will figure out number of outputs from the Y test or Y train. And X train, it will figure out also number of inputs from this one. It will get those numbers from here. So we have 3 outputs. So the output layer will be like this one. And the input layer, it will be like this one. We have 4 inputs, so it will be like this one. So this one will be X1, X2, X3, X4. Outputs here, it will be Y1, for example, Y2, Y3. And we will make those connections, right? We will have those connections. Sorry. So it will be like this. Connections. Right? It will be like this. So the dimension of this weight, this one, it will be 4 times 5. It will be 4 times 5. This one, V, for example, it will be 5 times 3. 5 times 3. We have here bias, correct? So it will be like this. So I will train my model using X train and Y train, and I will use X test for making some predictions, and I will use those Y predictions to find number of misclassified cases. So number of misclassified cases will be Y test not equal to Y predict. This one. We try to get the summation of the cases where Y test not equal to Y predict. When Y test not equal to Y predict, it means this is a misclassified example. For example, divided by the length of Y test, multiplied by 100. This one will be the prediction error. If you want to plot the confusion matrix, so the confusion matrix, we need to get the confusion matrix for Y test and Y predict, right? And after that, you can just plot it, correct? So we will get the confusion matrix here for the train and test. So this is the predicted label, and this is the true label, for example. I have 3 classes. We have class 0, we have class 1, we have class 2. This number, what does this one mean? It's 40 from class 0 classified as 0. This one, 37. I guess we didn't use stratify here because number of classes is different. No, this is correct. We have 40 from class 0. From class 0, we have 40. From class 1, we have 37 plus 3, which is 40. From class 2, we have 40, right? So how many from class 0 classified as 0? We have 40. So in fact, for class 0, the accuracy was 100%. From class 2, class 1, for example, we have 37 out of 40 classified as 1. And unfortunately, we have 3 from 1 misclassified as 2. So we have confusion here, right? We have some confusion in this class here. For class number 2, we have 0 classified as 0, we have 0 classified as 1, but we have 40 classified as 40. 40 from class 2 classified as 2. Correct? So for the training test, in fact, the accuracy is very high. We have only 3 misclassified. I mean, we need to maximize all numbers across this diagonal. We have here only 3 classes, 3 misclassifications. Right? For the test set, the accuracy it's almost equal 100% because from each class we have 10. Because the total size of my data set is 150. We have 40 for training and 10 for testing. So this one will be 10, 10, and 10. When you read this confusion matrix, it means 10 from class 0 classified as 0, 10 from class 1 classified as 1, 10 from class 2 classified as 2. So the accuracy, in fact, here it's 100%. If you want to get the accuracy, so it will be 10 plus 10 plus 10 divided by 30. So it will be 1 multiplied by 100, so it will be 100%. So we need to use MLB for MNIST dataset. Now we need to go. Do you have any question for this MLB for Iris? Any questions? Can you hear me?
Yes, I hear you.
Yes.
Okay,
It's okay.
Oh, it's okay. So now we need to use MLB for MNIST dataset. MNIST dataset, it's handwritten digits, which has a training set of 60. It's already divided, by the way. In if you will use it, if you will import it from Scalar, it's already divided. So it's divided into 60,000 examples for training and test, and 10,000 examples for test. So the digits have been size normalized and centered in a fixed size image. I mean, if you can go into try to Google MNIST dataset, it has been done by many people, and they try to fix those images into a fixed size. I guess it's 28 times 28 pixels. It's a good database for people who want to try learning techniques and pattern recognition methods and real-world data while spending minimal effort on pre-processing and formatting. If you want to collect this data for yourself, by yourself, it will take a huge amount of time. So we are lucky that we have access to such data sets for testing our algorithms. So it's all digits from 0 to 9, and it has been written by many people. You can get more explanations about it. And each digit is 28 times 28 pixel gray image. So it's a gray image, and the size of each image is 28 times 28 pixel values. So so each digit from those, for example, it's like this one, and it's 28 pixels times 28 pixels, right? And it's a grayscale, which means each pixel value, it's a number between 0 and 1. And it's a gray image, which means it's one channel. It's not 3 channels. It's not RGB, but it's a grayscale. We have grayscale and we have RGB image. So if we need to use MLB classifier with MNIST dataset, we need to import MNIST first from keras.datasets. It's from keras, right? So we need to get MNIST dataset from keras.datasets, right? We need to import it. We need to import MLB classifier from neural network, sklearn.neural network. We need to get this model, MLB classifier, from here. We need to import confusion matrix from sklearn.metrics, confusion matrix. We have also a nice function for plotting the confusion matrix. It's called plot_confusion matrix from sklearn.metrics. So this is all, right? We have a function also called the toCategorical. And this toCategorical, it's a function which is used to convert categorical we will see. I mean, maybe the target feature, I don't know why we need to use it if it's not. Okay, so this is each image. So first we need to import this data sets from keras.datasets. So it's mnist.load data. We import mnist from the keras.datasets. So it will be mnist.load data. So it will be already divided into xtrain, ytrain, xtest, ytest. You don't need to shuffle, don't need to do anything. So when you upload it in this way, the training data set will consist of 60,000 examples, and the test set will consist of 10,000 examples. We will use this one for training, we will use this one for testing, and it's enough for training and testing. It's enough for hold-out validation. If you want to plot the size, you can just print the size of the training set and ytrain and xtest and ytest. The shape of xtrain, it should be 28 times 28 times 60, right? So this one, because each image is 28 times 28, so it should be like 28 times 28 times 60,000 images, right? And we can plot some images. So for example, I can just, we have xtrain, for example. You can plot image show, because it's image. In fact, you can just use a function which is called image show. xtrain, for example, if you want to plot 10 images. So 10 images, which is 5 times 2, like this one. So I'm plotting all images from in this range, from 0 to 9, for example, right? xtrain. So because it's shuffled, right? So it's a 50419 to 1314, for example, right? So the shape, you need to prepare your data for training, because we will use feed-forward neural network. So my feed-forward neural network cannot work with images. In fact, it's not deep learning. When it's deep learning, we can keep this one as it is, right? So in deep learning, when this one is image, we can just use this image as it is in deep learning, because we use those convolutional layers, for example, and those convolutional layers, they can work on the image as it is. So we need to keep the image as it is when we are working in deep learning. But when it's a feed-forward neural network, it cannot understand the image. We need to work at the pixel level. So we need to convert this one from this shape into another shape, right? We need to convert it into a vector, not a matrix. This one, it's a matrix now, it's 28 times 28. But in fact, we cannot use this one with feed-forward neural network, and we need to change it into another shape. So we need to reshape the data into this dimension. So it will be 60,000 images, but we will convert each image into a vector of size. We will flatten it. You can just imagine that we are flattening it. So it will be 28 times 28. And it's a grayscale, in fact, and it's the pixel value has a number between 0 to 255. We need to normalize it. So we will just divide each pixel value by 255. So in this case, we will normalize it. So first, we need to flatten it, right? We need to flatten. It's very, very important to flatten it before working with feed-forward neural network. It's the same also in deep learning. We will do it with after convolutional part. We have the classifier. When we have the feature maps from the convolutional part, we need to flatten it as well. But we will do it here because we don't have any deep learning part here. We don't have any convolutional layers. But my model cannot work with this image as it is now, and we need to flatten it using this reshape function. We know that the size of the training set is 60,000, so we need to flatten it into this format. So in fact, we will convert all those images into one large matrix. It will be like this one. So it will be like this one. So the image one, for example, or example 0, 1, 2, until we go to 60,000. So the first row here, each row here will be one image. Each row here will be one image, right? So the length of this one, it will be 28 times 28 pixel values, right? So we will just we will flatten it, and we will put it flat like this one, right? Each image will be one row in this large matrix. So this is the training. For the test, it will be the same, but it will be 10,000. So it will be 0, 1, 2 until 10,000. And also the size of this image will be 28 times 28. So we will just flatten it. So we will do the same for the test set. So the test set will be 10,000 times 28 times 28. We will flatten it, and we will divide each pixel value by 255. Y train and Y test, it's one column. In fact, I mean, if you look into this data set here, the Y train and Y test, it's one column, and this column has the index of the image, the index of the class. So if this is class 0, it will be 0. If it's image, if the digit is 5, it will be 5. If it's 9, it will be 9, 8, 7, 0, 2, 4, 5, and so on. So this is the label. In fact, this is the label. This function, which called the two categorical, in fact, we converted this one from this shape into a categorical. So it will be converted. Yes, I got a question from Christian. Yes, please.
Hi, sorry.
Yes.
To interrupt.
Yes.
I was just thinking that we usually have two alternatives, that you could have 10, you could have a dimensionality of 10 in Y, where each label could be 0 to 1.
Yeah, one hot encoding. We call it one hot encoding, right?
One hot encoding, yeah, right.
Yeah.
Which would be the best?
One hot encoding, definitely. It will be the best.
Okay. So
right.
Could it be an option to convert this type of Y to one hot encoding before we train?
Yes, definitely. Yeah. We must do this. In fact, in this case, we will have 10 outputs. So our feed-forward neural network, it will have 10 outputs, and we need to use. But I don't remember two categorical. What is the function of this two categorical? It will be converted into one hot encoding. This function, in fact, it converted into one hot encoding, right? So we will just
Yes.
go to the next slide and see. Just 1 second. But it's important to do this one-hot encoding. Otherwise, it will be a problem because we will go to the next slide. Okay. Maybe we will open the code and try to. Okay. So just imagine now this two categorical. Can you check it? Because it will convert it into one-hot encoding, I'm sure, right? So we will convert this one from this. It will not be 1 column, but it will be 10 column, right?
Yeah.
And it will be zeros everywhere except 1 at the same index of this class.
Exactly.
We call it one-hot encoding. So we have this MLB classifier. We need to select. We need to select the optimizer again, right? So we have this MLB classifier. We imported it. We need to select our solver. Solver equal SGD or the optimizer, right? Usually they call it optimizer or solver. So the activation function, it's a logistic, right? You can use another active. If you want to use RELU, it's okay. RELU, it will give you much better results. For example, this alpha, I don't know what is alpha in fact. I don't know what is this one. Hidden layer size. In this case, do you see this number? It's 130, which means we will use 2 hidden layers, right? This one means we will use 2 hidden layers. The size of the first hidden layer, it will be 100, and the size of the second hidden layer, it will be 30. Random state equal 1, maximum number of iterations. This one for printing the output from the training process. And learning rate, initial learning rate equal 0.01, and this tolerance equal 1 multiplied by 10 to the power of -4. We will use X-train and Y-train for training. After doing this training process, we need to get the score. So it will be MLB. I prefer to call this one model, just model. So model.score, X-train, Y-train for the training set. You will get the accuracy, the training error or training accuracy for X-train, Y-train for the training set and for the test set. So we will get the second number. Y-predict, it will be, if you want to get the predictions for the test set, so it will be model.predict, and the input will be the X test. The output will be Y prediction. If you have Y predictions and if you have Y test, we can get the confusion matrix. After that, we will plot the confusion matrix, right? We have here, okay, because ytrain.arg max MLB predicts. I guess the prediction, because we used this logistic function, so the output will be a number between 0 and 1, right? So we will get 10 outputs. We will have 10 outputs. It will be like 10 outputs, like this one, a vector of 10 outputs. So the correct class will be the one which has the largest value. So this one means return the maximum, the index of the maximum output. So maybe one will be 0.01, another one will be 0.5, 0.4, I mean the summation will be equal 1 because, right? So in this case, we will select this one as the class. So the class in this case will be 01, it will be class number 1. So the digit here will be digit number 1. This argmax function. We will clear. We need to go to the example. So at the end, first, before doing this, we will get this confusion matrix for the training and for the test set. And as you can see here, we have 10 classes, right? We have 10 classes. True labels, it's 10 classes, and the predicted labels, it's also we have 10. And also those numbers across this diagonal, we try to maximize those numbers. So for example, here we have 974.0 classified as 0. As you can see here, we can just select those numbers here. I mean, for example, it's 0, it's 8 and 9, for example. Remember, we are starting from 0 to 9. So for example, here, we have this number, which is 946.9 classified as 9, right? We have a problem here. We have 0, 1, 2, this one 3 and 4, right? You can see we have some confusion because some 9 classified as 3, some 9 classified as 4, and the 9, 3, and 4 they are close to each other, right? So we can understand why we have some confusion here. right? And also the same, also 8, also sometimes people write 8 like 3. So we have some confusion between 8 and the 3 and the 8 and the 4, some confusion here. So the confusion matrix is very good tool for, giving us good understanding of. We have also some problems here. For example, 27.9 classified as 0, correct? So we have some problems here with 0, in fact, because many digits can be misclassified as 0. For example, sometimes the 6 can be classified as 0, 8 classified as 0. Maybe people write it quickly, so it's hard to differentiate between 0 and 8 or 0 and 9. So as you can see here, we have a problem in this column, right? Because there are many digits can be confused with 0, can be misclassified as 0. 27.9 classified as 0, 48 classified as 0, 29.7 classified as 0. So we have a problem in 0, in fact. We have a problem in this. And it's the same also for the training set. Also, we have a problem for this one here. There are some confusion. Many numbers can be misclassified as 0, but otherwise it's fine because it's okay everywhere except this column, and we have some small problem here. So at the end, we can check the accuracy. So the accuracy for the training, it will be 99%, and for the test will be 94%. But again, this accuracy is not correct. We should not represent it. We should not represent it in this way, right? Because this is a single number. We cannot just use a single number for representing the test accuracy, and it's better to represent it as a mean value, an average plus minus standard deviation, or we can use confidence interval. Yes, Christian? And you have a question?
Sorry, I forgot to lower my hand.
Okay. Yeah. I need to go to the code so we can check. We need to check. Yes, but is it possible first before going to the code to go to Keras? Just I want to show you the example in Keras first before we go to the code, because we don't have that much time. I just need to clean. Okay, so Keras, if we need to use MLB from Keras is very nice tool, in fact. So in fact, we need to use, we just import also MNIST from Keras.dataset as we did last time, right? In this model, there are two ways, in fact, to do it in Keras. There is something called sequential API. We can just focus on sequential API at this moment. We can just use sequential API, import it from Keras.models. So from Keras.models, we need to import sequential API. Those layers, we call it dense layer, in fact, right? So the model will be sequential. We will use sequential API for building a model, but this model consists of layers. So we need to import something called dense layer from layers. We need to import a dense layer from layers. We need to import this two categorical from Keras.utilities, for example. We have the confusion matrix, it's the same. So first I need this is the classification model. We have number of classes. The number of classes will be the shape of Y train, right? Model equals sequential. We need to build the model. So model equals sequential. We use sequential API. And in this model, we will add number of layers. So the first dense layer will have activation function called RELU, for example. So this is the activation function. You can select any activation function. The input shape will be 28 times 28, and it's flattened, as you can see here. Because each image it's 28 times 28, but we need to flatten it, right? Because the input will be like this one. I mean, this is the input. I cannot deal with image because the input will be like this one. If this is a hidden layer and this is the input layer, so I need, in fact, to put it like this one. From x1 until x28 times 28, right? So we need to flatten it. So input shape will be 28 times 28. This is the number of neurons in this hidden layer. So it will be 350, for example, correct? It's up to you. You need to select this number. I mean, it's by, you need to do this. The second hidden layer, I will add another dense layer, and this dense layer, the activation function also will be RELU, and the number of units will be 50, right? You don't need to define inputs because inputs will come from the first layer. We need to define the input shape only in the first hidden layer, correct? Just here, we need to define the inputs, the size of the inputs, because it has not been defined before. So we need to define it only one time here. So here, we need to define only number of units. We don't need to define number of inputs because the number of inputs will be 350, right? So it will come automatically this one. The output layer, it will consist of number of classes. Number of classes will be the shape of the Y train. I mean, number of classes, and the activation function. I mean, in the output layer, in fact, it's better to use softmax. We call it softmax layer because the softmax layer, it will calculate the probability that this example belongs to this class. So now we build our model. We use the sequential API. We added 2 hidden layers, 1 output layer. So this one, it's 2 hidden layers, and this one, it's 1 output layer, or people call it softmax layer. You need to compile this model. You need to select the loss function. So the loss function will be categorical cross entropy because we have 10 classes. The optimizer, we use the Adam optimizer here. If you want to use another, it's okay. And the accuracy metrics, we have this accuracy metrics will be accuracy and error, for example. This is model summary. This is function called model summary, for example. It will give you all details here of your model, number of parameters in this model, for example. The output shape. I mean, the output shape of the first dense layer, it will be 350. The second, it will be 50. The third will be 10. You see? Which means this function, in fact, 2 categorical, it creates 1 hot encoding of this categorical variable. So this function 2 categorical, it creates this 1 hot encoding of this categorical variable. So when we use the 2 categorical, in fact, the targets was numbers from 0 and 9, right? So it was 1-dimensional target, 0, 2, 3, 4, 5, 9, and so on. So it will be, when we use 2 categorical, it will be converted from this form into 1 hot encoding. So it will be 10 column, and it will be 1 when it's 0, for example. It will be 1, 0, 0, 0, 0. When it's 2, it will be 0, 0, 1, 0, 0, 0. It will be converted into 1 encoding. 3, it will be 0, 0, 0, 1, and so on. So it will be converted. We use this function from keyrest.utility to convert a categorical variable into 1 hot encoding. So the output shape will be 10, 50, 350. If you need to calculate number of parameters, we did that before, I guess, right? So if you want to get this number, it will be 350 multiplied by the number of inputs, which is 28 times 28 plus bias, right? Maybe I can do it. So if you want to get this number, how can we get number of parameters in this layer? Right? This is first hidden layer. We have an input layer, but I mean, input layer does not make any thing. In fact, it's just to transfer inputs to the next hidden layer. So if number of units here, it's 350, and the number of inputs to this one will be 28 times 28, right? So if we need to get number of parameters here, it will be 28 times 28 times 350 plus 350. Can you multiply this number? So a calculator. Can you try to? So it will be 28 times 28 times 350 plus. No, why is this number very large? 28 times 28 times 350 plus 350. So equal 54. Why? It's a very strange number. Yeah, it's very large. And can you try to get this number, please? So it's a 350 times 28 times 28. Yes, equal to, yeah, plus 350. Yes. 247. Yes, it's this number, if you can see it here, right? Yeah. So it's this number equal 274,750. So this is number of parameters of the first hidden layer. If you want to get number of parameters of the second layer, it will be 50 times 350 plus 50. If you want to get this number, so it will be 50 times 350 plus 50. You will get this number. This one is easy, so it will be 10 times 50 plus 10. So it will be 510. So just remember, we use the sequential API to define our model. We add dense layers. I mean, we will use the same function here in deep learning, but instead of using dense layers, we will use convolutional layers and the dense layers as well, right? So the activation function in the first layer, it will be ReLU, and the softmax. It's of course, it's important to use the softmax all time in the last layer. We call it softmax layer. This is a layer which will make decisions, and the softmax layers, it is used to calculate the probabilities that this example belongs to this category, for example, or class. and the summation of the outputs will add to 1, right? So we will use categorical cross entropy. We will use this optimizer. So this is model summary. We got all those information. We will fit the model. We will train the model using X train, Y train, number of epochs equal 100, batch size equal 512. This number is critical when you have low memory, for example. So the size of the data set here, we have 60,000 examples, right? Correct? So, and those images, so the size of the batch size, it's based on my memory. How can I calculate it? We have the images, it's 28 times 28 pixel values. So if each pixel is stored in 3 bytes, so it would be 28 times 28 times 3 bytes, for example, divide it by 1000 to convert it to kilobytes or megabytes, whatever. And at the end, you will see how much batch size your computer can accommodate, for example, or so it's about your memory, right? If you are working with images, high definition images or videos, for example, so this number will be critical. So anyway, this batch size is very important. And using this batch size, it means we are using mini batch gradient. And in this case, we will do one update each batch, right? So we will calculate the gradient. We will have the average gradient each batch, and each gradient we will do adjustment or updates one time each batch. So if you want to see how many times we will update the weights of my model, it will be 60,000 divided by 512 multiplied by the number of epoch, correct? After doing this modeling stuff, we will evaluate our model. So we have this model.evaluate for the test set. The input will be X test, Y test, and after that we will print out those numbers. So maybe I need to clean. Okay, so after doing this, using we got much better results compared to sklearn, but because this model is more complex, I mean, it has more two hidden layers, but number of it's different optimizer. We used here different optimizer with different here also different activation function in the other, because as you can see here, for the test set, we don't have the problem here in 0, for example, the confusion with 0 don't have this problem here, as you can see here. We don't have this problem because we had a problem here in the last example, but we don't have this problem here, but we cannot make comparison between the two because the two models are different, right? I mean, number of units is different. It's the same number of hidden layers, but number of units in each hidden layer is different. And also the activation function is different. It's smart to use RELU because RELU will perform better with vanishing gradient. So as you can see here, we try to maximize those numbers. And at the end, also, we will get this loss using a categorical cross entropy. We have the loss and the accuracy, but I cannot see it in my computer because I have something here. So yeah, I guess this is all for today. So we can open one example. Saving and loading. It's at the end also. It's just something at the end. We need to save and load our trained model, because sometimes you train a model which takes too much time, right? I cannot go back to the last slide, sorry for this. But we need to learn how to, store our model, because sometimes it takes too much time for training your model, and you don't need to waste this time again. You don't need to spend that time again. So it's important to save your model in some place. So models that take long time to train. Can you see my screen? Yes. So it is required to save the trained models, so we don't need to have to train them each time, for example. So it's important to do this, to store your model somewhere, and also maybe you are building a model for a company. So in fact, at the end of the day, you will give them a file which contains all those weight values. So people can just install this model in their computer. You don't need to spend much time again for doing this again. So I will go to this example. Maybe Kiras, should we take the one from Kiras, for example? We can go this one from Kiras and just open it. want to share only my screen. This too. So this is the model. Can you see my screen? So can you see my screen?
Yes.
Okay. So this is the model. We need to run that part. So we imported MNest from keras.datasets, sequential API. We imported it from keras.models, dense layer. So we need to import dense layer from keras. When we go into deep learning, we will see other layers. We have flatten layer, and also we have the CNN layers. Two categorical. This function is very important because this function will do the one-hot encoding for us. It will convert a categorical variable into a one-hot encoding, so we can. We have confusion matrix, precision score, record score from sklearn.metrics, for example. We use the MNest. We don't need to use train test split because the data set is already divided into a training set and a test set. So this is the length. I mean, this is the size of the training set. It's 60,000 times 28 times 28, and the test set is 10,000 times 28 times 28, right? This is some examples. This is the classification model. So sequential, we use the sequential API, model equals sequential API. This is the first, hidden layer, dense layer, has 350 units. It will be nice to visualize. I guess there is a tool, in fact, for visualizing those models. So I will try to link this one to it so we can see the model, how it looks like. The second hidden layer has 50 neurons, and it uses ReLU. We need to define the input shape only for the first hidden layer because this is the most important part. For the second layer, we don't need to do this because it will get this number automatically from this layer, which is 350. With the soft max layer, they call it they call it soft max layer, and it will calculate the probability that, for example, this example belongs to 2, or this example belongs to each category, for example. We will use categorical cross entropy. We will use this one. As you can see here, this is the summary of the model. Total parameters, 292,000 parameters. And it is the summation of those variables, in fact, right? This is a very simple model. Trainable parameters and non-trainable. All parameters are trainable, correct? We don't have any non-trainable parameters here. We can have non-trainable when we try to freeze some layers. So, for example, we can freeze some parts, or we can freeze 10% or 20% of the parameters. So, in this case, we will get some number in this non-trainable parameters. We will train the model for 100 epoch. So, and after completing this training process, we will calculate Y predict for the X test. I want to show you if we can print. If we can print this one, Y test, maybe we can print Y test. Maybe just from 0 to, I don't know, maybe it's like this one, could be. I hope it will work. So you can just see the one-hot encoding. Maybe because it's busy here. Of course, when you are using Google Colab, you can connect to a hosted runtime, for example, custom local runtime. So you can select also if you want to use a GPU or something, host runtime. If you want to use a GPU, you can go to runtime here and change runtime type. For example, you can select this hardware accelerator. You can select a GPU, for example, if it is available. And in fact, you can create an account here and pay little money and get very Oh, sorry, but in this case, it will, this is bad because it will reinitialize. I need to do it one more time. So it will do that part. Do you see here? This is the one-hot encoding, right? So if I want to print Y test before and after, sorry, I will just do it here. So you can see that we do one-hot encoding. So Y test, Y 0 to 1, it cannot print only. So as you can see here, too many indices, I don't know why. Maybe. So do you see it's 7, for example, right? When it's 7, the index here, it's 0, 1, 2, 3, 4, 5, 6, 7. It's 1 when it's 7, right? So this is the one-hot encoding. So this function, which is 2 categorical, it converts this categorical variable into one-hot encoding, right? So it converts 7 into this one. After that, we will build our model. And it will train, of course, it will take too much time for training. So maybe it's about faster now because we use the GPU, for example. So if you want to change your runtime accelerator, for example, you just go here and try to change runtime type. So you can select a GPU, for example, or TPU. So now it's much faster. Of course, we need to plot also the accuracy and loss for each epoch. Validation set, we have a problem here also. We have the validation loss. Yes, we have validation loss. Good. So we can see if the model is overfitting or not. So thank you. Okay, so the loss equal, accuracy equal. So the accuracy equal 98%. We will do this testing because we need to plot the confusion matrix. Yes, we have the confusion matrix here. And we can also get this precision recall, precision accuracy, correct? And this is the confusion matrix. If you want to plot the confusion matrix, you get those numbers here as a matrix, and you can plot those numbers here also in this confusion matrix. We can do it for training and testing set. Yes. Yeah, just please let me know if you have any questions. Just keep it like this, and I want to save it to copy and GitHub. Okay, so please, do you have any questions? Any questions, please? So now we finished for today, and I mean, next time we will, I will try to prepare something for this model evaluation, for example, because we need to get this confidence interval, for example, so you can avoid getting any questions from reviewers or examiners, for example, if you are communicating your results to people, for example. So we need to communicate our results in the best way. Yes. So thank you very much for today. But
sorry,
yes, please.
can I ask organization question?
Yes.
Very quickly. Yeah, because of the time difference, I will be not able to attend the next classes. I was wondering if you have any records for the next lectures. I mean,
okay, yes, we do recording today for the 2 sections, morning and I mean we have this YouTube link, for example. I will put it in so we will do it each time. And also, if you prefer another time, just let me know. So if Friday is not fitting all of you, we can select another day. I don't have any problem for.
Yeah, but that's just temporarily because I'm for a business trip. I'm flying to Mexico, and because of the time difference, I will be not able to attend the next 3 lectures. So I was wondering if